Good afternoon, everyone. So, as you all know, this is problem solving session for the Computational Fluid Dynamics course. So, the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, and this live session is handled by myself, Ankara Karthika from the Department of Chemical Engineering, IIT Hyderabad. So, it has been happening every Saturday from 3 p.m. to 5 p.m. So, yeah, we'll start today's class now. If there are any doubts, you can ask at the end, or in between. If you have any doubts, please unmute yourself and ask. I might not check the messages in between the class. Thank you. So, and one more thing, as you might have seen that exam announcement came. So this exam is computer based test, and there is like calculator trial, like how to use the calculator online is available in the NPTEL. So you can check that and be familiar with that, so that it would be helpful for you in the exams if any questions come like that wherein you need to solve it using calculator. So let us now move on to the class. So we have been almost covered 12 weeks problems till now. So first we started with the calculation of flow in a rectangular duct and in triangular duct. So we saw how to formulate the equations and how to solve them. So in that class we were familiar with finite difference approach and finite volume approach, like how it can be implemented when we are given a system to deal with. Later on we were seeing about what is CFD. CFD is nothing but how to solve the equations to get the variables in a system. Like if we are dealing with a fluid flow in a system, we need to know the variables at every point. So for that point, what we do is we solve the governing equations, mainly the continuity equations and the momentum balance equations. And if there are energy involved, we go with that as well. And if sometimes when we deal with reactions, so species conservation equations also come into picture. So basically CFD is nothing but how we get the solution for those equations. So basically in week 3 it was about derivation of the equations governing fluid flow, and later we saw about the equations for incompressible flow and boundary conditions. So it is also necessary to get the boundary conditions, because only then we can solve for the system. For example, if we are heating a rod at one end and we need to get the temperature at the other end, we must, other than discretization and getting the equations, we must know some conditions along the boundary, that uh, near the walls we can impose wall boundary conditions, and in the inlet we know the temperature. So like that we need to know the initial and the boundary conditions. And later on it was about finite difference approximations. That is the basics of basic concepts of CFD. Apart from that, finite apart from finite difference approach, we also use the finite element approach and finite volume approach. So those are big advanced. And later when we are dealing with the finite difference approximations, it is also necessary to get the solutions. Once we discretize the system, we need to know um, how we will be getting the solutions. So for that we need to understand the consistency and stability. Only then we get the converse solutions. And later on we also dealt with Navier-Stokes equations for compressible fluid flows and for incompressible fluid flows. Like there are various methods that we dealt with. For compressible flows we dealt with beam warming method and McCormick scheme, and for incompressible fluid flow we dealt with stream function vorticity approach, pressure correction method, and artificial compressibility method, everything. Later on, once we get the discretization and once we apply some schemes, we need to go with solution. We need to get the solutions. For that we use a numerical approach. So that is we have now converted the partial differential equations, that is the governing equations which were in the partial differential forms, into a linear algebraic equations. So now after the conversion by using any discretization schemes, we need to now get the solution. So that solution we use the numerical techniques. So we can either go with basic methods or we can go with advanced methods. So depending on that thing, we have solved the problems by using numerical methods like Gauss-Seidel method, Jacobian method, successive over iterations, and so on. Like those concepts were we utilized, and later on it was about basics of finite volume method, including grid generation. So grid generation, we have covered things like structured grid, unstructured mesh, everything. And later in week 12 it is about turbulent flows and turbulence modeling. So in last week's class itself we have seen the practice problem from week 12. So today we'll just have some few problems from week 12 which will help you in solving this week's assignments, and later we move on to week 11 remaining problems, like solution to those problems. So now for books and references, we have Ferziger and Perick computational methods for fluid dynamics, and HC numerical computation of internal and external flows, and Pankar SV numerical heat transfer and fluid flow, and Verstig HK and Malal Sekara W, and Introduction to Computational Fluid Dynamics, the finite volume method, and Anderson JD computational fluid dynamics basics with application. So I have used Anderson book, so it will be very useful when you are dealing with basics. So if like it will be brushing of all the concepts, so it will be useful to learn all the basics related to CFD. And one more book that I felt is quite useful is Computational Fluid Dynamics and Heat Transfer by Tanhill, Anderson and Pletcher. So that's one thing. So you can like just be confident when you are appearing for exam, and just quickly revise all the concepts like from week 1 to 12, so it will be like you can do the exam well. Now let us solve week 12 problems. So first there is a case, and here is one figure. So figure 12.1 is this: unsteady turbulent developing flow of water with density 1000 kg per meter cube and viscosity 0.001 Newton second per meter square through a rectangular duct of dimension L into W meter H, such that L is larger than height and W is equal to 1.5 times of height. And inlet velocity is uniform across the inlet plane but varies with time as shown. Outlet can be considered as zero gauge pressure surface. So what is happening inside the system? We are now dealing with a rectangular duct flow problem. So inside this, what is flowing is water is flowing. Water is having density 1000 kg per meter cube and viscosity 0.001 Newton seconds per meter square. And the duct dimension is given such that L into W into H. So this is length because it is very much larger than height, and L is very much larger than height, and W is 1.5 times of height. So L is greater than W, W is greater than H, and H is smallest, L is largest. So L is largest, height is smallest, and width is comparatively 1.5 times of height. And inlet velocity is uniform across the inlet plane, that is it is uniform across the inlet plane, but what it is varying with, it is varying with respect to time. So V T is equal to V into 1 plus T power 1 by 2. So it is uniform across the plane, but with time it is varying. So outlet can be considered as zero gauge pressure surface. So this outlet we can use zero gauge pressure condition, that it is like exposed to the atmosphere like that. So now we'll go to question 1. In question 1 it is mentioned that in figure 12.1, so we are now dealing with all the questions with reference to figure 12.1. So if height is 2 centimeter, what is the value of V in for the flow to have a minimum Reynolds number of 50,000? So what is asked? If the Reynolds number is 50,000, what would be the value of V in, and velocity inlet is what, and height is given as 2 centimeter. So here we need to know that it is a rectangular duct. So it is a rectangular duct, it is not a circular pipe. So for that alone we need to make changes, but apart from that, if Reynolds number is given, we need to find the velocity. So options given are option A 1 meter per second, option B 2.1 meter per second, option C greater than 2.5 meter per second, and option D it is less than 0.25 meter per second. So we all know that flow Reynolds number is rho V d by mu, that is initial force by viscous force, rho V d by mu. And here we, since there is a rectangular channel and rectangular duct, we need to know, we need to use the hydraulic diameter. So for that we are calculating the hydraulic diameter, but apart from that we know the density of water. So rho is known, B we need to find out, D we need to calculate, and mu again we know it. For water the velocity is given, viscosity is given as 0.001 Newton second per meter square, and Reynolds number is given as 50,000. So only unknown remaining is V, and only thing we need to calculate is D. D is 4 into cross sectional area of the pipe divided by 2 times of wetted perimeter. So wetted perimeter is like, here it is, this flow is completely through the duct. So it is, this is height and this is width. So width plus 2 times of width plus height, that is the rectangular perimeter we are calculating now, 2 into A plus B. So 2 into H plus W, and cross sectional area is A into B, that is 4 into W into H. And later on we had W as 1.5 times of H. W value is not directly given, so it is 1.5 times of H, and H value is given as 2 centimeter. So now what we are doing, we are just substituting it over here, and D is equal to 4 into W, that is 1.5 times of H, and into H, so it becomes H square, divided by 2 into 2.5 times of H, that is H plus 1.5 times of H, that becomes 2.5 times of H. So that becomes 2.5 times of H. And now we are just substituting 4 into 1.5 times of H square divided by 2 into divided by 2 into 1.5 plus 1 times of H, that is 2 into 2.5 times of H. So on after that we get 6 divided by 5, 4 into 1.5, that is 6, and divided by 5, so it would be 1.2, and H square divided by H, it becomes H, and now we know the value of H as 2 centimeter, so H is 1.2 into 2, that is 2.4 centimeter we get, and it is centimeter. So later on what we do, Reynolds number is equal to rho V d by mu. So V is equal to Reynolds number into mu by rho into d. So Reynolds number is 50,000 into mu, that is 0.001, divided by rho into d, that is 1000 into 2.4 centimeters. So we are converting it to meter, 2.4 into 10 power minus 2, and we get the value as 2.083, and approximately rounding off it gives us 2.1 meter per second. So answer is option B, that is 2.1 meter per second. So what we are doing, we are asked to calculate the velocity inlet. If we need to know the, if we are known with the Reynolds number, we are now asked to calculate the velocity inlet. So for velocity inlet, we are just substituting in the Reynolds number formula. Reynolds number is initial force by viscous force, which is given by rho v d by mu. So in this particular form, we know Reynolds number, we know density of water, we don't know velocity, and we need to calculate d. Because it is not a circular pipe, we are just calculating the hydraulic diameter, and that is given by 4 into cross sectional area of the pipe divided by 2 times of wetted perimeter. So here cross sectional area of the pipe we calculate as W into H, and wetted perimeter 2 times of W into H. It is perimeter alone. And later we get it to be 1.5 times of H, and we get the value this, and with we know it as 1.5 times of H, so we substitute it in the hydraulic diameter, and later we put it back in the equation and we get the value as 2.1 meter per second. So I hope first question is clear. Now we'll go to question 2. In question 2, it is asked that we wish to simulate the flow through the duct shown in figure 12.1 using the K epsilon turbulence model. Which of the following statements are correct about Reynolds average Navier-Stokes equation? So what is given? We wish to simulate the flow through the duct shown in figure 12.1 using K epsilon turbulence model. Which of the following statements are correct about the Reynolds average Navier-Stokes equation? First one, we need to solve unsteady form of Rand's equation. Second, we need to solve unsteady Rand's equation because the flow is turbulent. And third, we can use the steady state form of Rand's equation because the equations are time averaged. So in question again, what is asked? The system given for us, we are going to solve it using K epsilon turbulence model. And while doing that, which of the following statement is correct when we go with Reynolds average Navier-Stokes equation, that is Rand's model. So first we need to solve the unsteady form of Rand's equation. This is true because like flow is developing and we are using the turbulence model. It be varying with time. So we need to use the unsteady form of the equation. And second, we need to solve unsteady form of the equation, unsteady Rand's equation, because the flow is turbulent. As I have said before, we are solving with that because in turbulence flow it takes quite an time. So we need to solve with the unsteady form of the equation. And third, what it is given, we can use the steady state form of Rand's equation because the equations are time average, which again we cannot use because like in the thing we are dealing with is not a steady state obtained form, so we cannot use that. So 1 and 2 options are right. We'll now check with the options given. So A is 1 and B is 2, C is 3 and D is 1 and 2. So as we have seen now, the right answer to this particular question is option D, that is 1 and 2. So I hope it is clear. Now we'll go to question 3. In question 3, it is asked that we wish to simulate the flow through the duct shown in figure 12.1 using K epsilon turbulence model. How many partial differential equations do we need to solve? So here what is this similar type of question we have seen throughout the course, that with every system and every domain how many equations we were asked to solve. Like maybe in exam also it might come, I'm not sure, but it is like just checking our understanding and application on different types of system. So basically, how many equations, partial differential equations, do we need to solve for a system? Generally, if what are all the equations we will be generally solving? We will solve for the continuity equation and momentum conservation equations for sure in all systems, wherever the flow is concerned. And after that, if there are energy transfer or temperature gradient existing within the system, we need to go for the energy conservation equation as well. And if there are reaction happening inside the system, we need to solve for the species conservation equations as well. So those species conservation equation, the number depends on the number of species present in the system, and energy balance equation there will be one. So here in this particular system there is no need for those two. So we will be solving for continuity equation 1 and momentum conservation equations 3. And after that, here we are using the K epsilon turbulence model. So we have two more, one for solving K and one for epsilon. So we have two more equations for turbulence. So on the whole, we have 1 plus 3 plus 2. 4 plus 2, it is 6 equations. Because we are dealing with a three-dimensional system, we need to solve for the xyz coordinate in the xyz momentum balance equations. We are taking all complete three. If the system is a two-dimensional system or whatever, then that number would be varying again. So now let us just look at the options. Option A 4, option B 5, option C 6, option D 7. So as we have discussed, the number of equations that we need to solve is one continuity equation, three momentum conservation equations, and two turbulence equations. So on the whole, we have 6 equations. So answer to this problem is option C, that is 6. We are now dealing with 6 partial differential equations. So in K epsilon turbulence model, again we are just going to deal with two more equations in addition to the existing 4 equations, that is the continuity equation and the momentum balance equations or momentum conservation equations. So we have, on the whole, we have 6 equations. So that is for question 3. We'll now go to question 4. In question 4, what is being asked? Which of the following statements is true about the turbulent kinetic energy variation within the duct for the problem shown in figure 12.1? So what is being asked? It is asking which of the following statements is true about the variation of the turbulent kinetic energy for this system shown in figure 12.1, that is the flow through the rectangular duct. Which of the following statements is true about the variation of the turbulent kinetic energy? So the first question, at a given location not close to any boundaries, turbulent kinetic energy will be increasing with time. And second statement, at a given axial location at a given instant of time t greater than 0, turbulent kinetic energy will be higher close to the center than close to the wall. Okay. So we are now given with two statements. The first statement, what it is saying, at a given location not close to any boundaries, turbulent kinetic energy will be increasing with the time. This is true because when we are dealing with walls, there will be so many factors, other factors that will be coming into play. But in the question, what was mentioned, the velocity is uniform across the plane, that is the velocity is uniform across the plane, but it was varying with time, that it was varying or increasing with time. As the time increases, the velocity, inlet velocity was also increasing. So because of that reason, turbulent kinetic energy will also increase with the time. We are not considering the location close to any boundaries because that would be again so many factors would be playing. So we can see that apart from the location closer to boundaries, the turbulent kinetic energy will be increasing with time. And second statement, at a given axial location and at a given instant of time t greater than 0, turbulent kinetic energy will be higher closer to the center than close to the walls. So what it is saying is at any instant of time after t greater than 0, turbulent kinetic energy at the center will be greater than near the walls. This we cannot put it forth because the system we are now dealing with is a turbulent system. So turbulence affects play. So on that basis, there will be so much fluctuations happening inside the system, and so we cannot say that it would be higher, like how it will be varying with position. We cannot just put it out directly. So options are option A 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So right answer is option A, that is first statement alone is right. Remaining statements, that is remaining statement, second statement is false because we cannot say about how it will be varying with respect to position. So we cannot comment on that. But first statement, it is apart from the boundaries. Here we are not mentioning how it will be varying with boundaries. So we are just saying at apart from the boundaries, turbulent kinetic energy will be increasing with time. This is because with increasing increase in time, velocity was found to vary. That is v into 1 plus t by 2 power 2, something like that. It was varying. So it was like increasing, velocity was increasing with time. Thereby the turbulent kinetic energy will also vary with time. So if we go back to the problem statement, what it is mentioning that velocity is varying with time as v into 1 plus t power 1 by 2. Sorry, t power 1 by 2. So obviously it is like varying in terms of some factors. So with some percentage it is increasing. So we can say that it is increasing. Turbulent kinetic energy will be increasing with time. So answer is option. First statement is right, second one is false. So accordingly, if we go by that, we can say that A is right, B and C and D or rest are false. So answer is option A. So just when you are answering questions, some questions might be asked to pick out all the right answers. So if that is the case, like in exam, in the exam, just be careful to read the questions and pick out all the right options. So if sometimes the questions might be twisted slightly. So now we will go to question 5. In question 5, it is asked that which of these are characteristic features of turbulent flows? Option 1, or always three-dimensional and always fluctuating. And option 2, it is high diffusivity. And option 3, do not obey Navier-Stokes equations. So in turbulent flows, which of the following statements are right? So first one, always three-dimensional and always fluctuating. And second one, high diffusivity. And third one, do not obey Navier-Stokes equations. So we can one thing that we can rule out here directly is that third statement. Third statement is a false statement because we cannot say that turbulent flows will be turbulent flows are deviating from. We cannot say that turbulent flows would not obey Navier-Stokes equations. That is a false statement. So third one is a false. Like those are also the equations which we will be using, like, and we will be solving for those. So it is not that they are Navier-Stokes equations only applicable in certain conditions. Like, I mean, it is not applicable for turbulent flows. We cannot say that. So the first statement, coming back to the first statement is mentioning that always three-dimensional and always fluctuating. So that is true because like we can only visualize that in three-dimensional space and it would be always fluctuating it. Like all the parameters would be varying, so that's why it becomes complicated to solve systems when concerned with turbulent flows. And second one, it is high diffusivity. So again, this is also true because if you imagine the turbulent flow systems, things would be moving randomly, and it would be very fluctuations will be there, variations will be there, and because of that it would be high, like so many like high diffusivity can also be observed. And third statement, it is do not obey Navier-Stokes equations, which is false because we cannot generalize that. So I mean we cannot say that. So only one and two statements are right. So now let us look at the options. Option A, it is 1. Option B, it is 1 and 2. Option C, it is 1 and 3. Option D, 1, 2 and 3. So in all these options we have one common, and again we know that second statement is also true, but third statement is false. So now we need to pick out 1 and 2. So right answer is mentioned in option B, that is option B is stating 1 and 2 as right. So now the correct answer for this particular problem is option B, 1 and 2. So the characteristic features of turbulent flows is it has always fluctuations and high diffusivity would be observed. So we are going with 1 and 2 in option B. So these are the 5 problems for week 12 actually. So like if we look if we go through it once again, first one is a rectangular duct problem, and because it is a rectangular duct, we are in the first question we are asked to find the inlet flow velocity, and we are given the Reynolds number. So if Reynolds number is given, which is nothing but rho v d by mu. So d, we know it as a pipe diameter when we are dealing with a circular pipe. But in the rectangular duct, we need to find the hydraulic diameter, which is given by this formula, and we calculated and we substituted back. And then we use the W as, I mean, W is given as 1.5 times of H, and rest of the things we know H is given as 2 centimeter. We substitute everything and we get the value of inlet velocity as some 2.1. And in second question it was about time averaged, sorry, where what would happen when we use the Reynolds average Navier-Stokes equation. So we are not, what we are doing is we are dealing with unsteady form of the equations. So we need to solve for the unsteady form of Rand's equations, and we need to solve the unsteady Rand's equations because the flow is turbulent. So in the question statement itself it is clearly mentioned that we are dealing with a unsteady turbulent flow problems. So here it is mentioned that unsteady problem and turbulent flow problem. So we are using Rand's equation. So in that case we need to solve for the unsteady form of Rand's equations, and we need to solve because flow is turbulent. Third statement is false because the flow is not a steady state problem, and because equations are time average we cannot generalize that, because in the question itself it is clearly mentioned that the problem we are dealing with is unsteady turbulent flow problems. And in third question it was about number of partial differential equations that we need to solve. So in the question it is a rectangular duct, so we have a three-dimensional problem. So one continuity equation and three partial differential equations for the momentum balance. And now for turbulence model we have two more equations, that is K and epsilon. So that is nothing but turbulent dissipation and the turbulent kinetic energy. And we have two more, so on the whole we have 6 equations. So that is how we got 6. And in question 4 it is about turbulent kinetic energy variation within the duct. So we have seen how it will be like apart from the region that is closer to the boundaries, in all other regions turbulent kinetic energy will be increasing with time. So but we cannot generalize how it will be near the walls. And in question 5 it is about the characteristic features of the turbulent flows. We saw how it is about always fluctuating and always three-dimensional problem with higher diffusivity. So these are the week 12 problems. Now we'll go back to week 11 problems and we'll check again. And before that I'll just insert page number or the slide number. It is a bit confusing, that's why. So this is week 11 assignment problems. Here we are given with two grids. two-dimensional domain, we are given an example of grids. So the system is almost the same, like this is going like this and this, and we have used two different meshing. Here it is a structured mesh and here it is an unstructured mesh, because you can all see that meshing is quite different over here. And the coming questions coming after this are based on this only, like these two structures. So the first question is that for the grids shown in figure 1, which of the following statements is true? So similar question we have seen in last week also. So now we are asked to identify which of the following is a structured grid and unstructured grid. So before itself we have identified how 11A is a structured grid and 11B, that is, or 1A is a structured grid and 1B is an unstructured grid. Here it is a structured grid because we can identify the adjacent grid or the neighboring grids based on some points or some means from the present cell. However, if we are here and we need to identify the neighboring cells, it is quite difficult by using this, so we call it an unstructured mesh. So on that basis, now let us look at the options given. Option A, figure 1A is structured grid and 1B is an unstructured grid. And option B, figure 1A is an unstructured grid and 1B is a structured grid. And both grids are structured grids, option C. And option D, both grids are unstructured grids. So the first one, for grids, we have now rightly identified the 1A as structured grid and 1B as an unstructured grid. So here, which is matching with our answer is that option A is matching. So answer to this problem is option A. In last class there were two more statements, so I am just saying this to say I'm just including this to say that questions can also include such forms, like in option C and D it can be like figure 1A, it's a structured grid and it can be transformed into unstructured grid as well, and 1B is an unstructured grid and it can be transformed to a structured grid as well. So those statements here however is not suitable because the system or domain is same, like here the domain what we are dealing with is same, so here it is not possible. But if the system is different, it can, we can do that, those things as well. I mean those options might also come, so you must be careful in those cases. So now we are now clear with that 1A is a structured grid and 1B is an unstructured grid, because in 1A we were just able to identify the neighboring elements from the present cell on the basis of some points like I, J, K addition we can travel to the neighboring cell. But in 1B, that is here, we cannot just travel from this particular cell to another cell by means of some identification I, J, K. Rather than that, we need to have the cell lists. That is, if this is the concerned cell, we need to have the cell list to be able to identify the adjacent cells. So that is what is asked in this question. Now let us move on to question 2. In question 2, it is given that the grid given in figure 1A is an example of which of the following. That is what is being asked. The grid given in 1A is an example of which of the following. So first one, local grid refinement in an unstructured grid. Just a minute. So what we were saying, A grid given in figure 1a is an example of which of the following? Local grid refinement in an unstructured grid. Option 2, local grid refinement in a structured grid, and grid refinement at the wall boundaries. So we can say that option A it is given in 1 only, option B 2 only, option C 3 only, option D 2 and 3. So now let us just have a look at this figure once. Let me just put the figures for the next few questions as well. So this is the question. So in figure 1a, the grid given is an example of which of the following? Option 1, local grid refinement in an unstructured grid. Option 2, local grid refinement in a structured grid. Option 3, grid refinement at the wall boundaries. So this is the 1a figure. So here it is, what we can see, it is a structured grid. So option 1 is false. Second one, it is local grid refinement in a structured grid. So here it is, cells are not uniform. So like here in few areas, like here the cells are refined so much, and here in the this way the length is more than the height. So we can say that local grid refinement has been there, and since it is in a structured grid, option 2 is correct. Whereas in option 1 it was mentioned local grid refinement in an unstructured grid. So first statement is false and second statement is right. We are now doing the local grid refinement in a structured grid. So second statement is true. Third one, it is mentioned that grid refinement at the wall boundaries. So are we seeing any refinement at the boundaries? No, like grid refinement is not at the boundaries but rather in the middle cells or so. So here, especially in this particular region, we can see that grid refinement has been done. So local grid refinement has taken place but in a structured grid and not near the wall boundaries. So first statement is false, second is true, third is again false. So looking at the options, option A 1 only, option B 2 only, option C 3 only, option D 2 and 3. So it is like option B is the right answer because it is mentioning only 2. So option B is the right. I hope it is clear. Now we will go to question 3. In question 3, what is given? The grid given in figure 1b is an example of which of the following? So again, what is being asked? So here it is in an unstructured mesh, and like in a previous questions, 3 statements are given. So here we can say that the completely unstructured mesh is inside the regions, but near the walls there is a grid refinement. So near the wall boundaries there is a grid refinement in this particular figure, but not anywhere locally. So first let us look at the options. Option 1, it is local grid refinement in an unstructured grid. So even though it is an unstructured grid, we do not see any local grid refinement. Rather, grid refinement is taking place adjacent to the wall boundaries. So not anything is happening locally. So option 1 is false. Option 2, it is local grid refinement in a structured grid. So again, the statement is completely false because we are not dealing with any structured grid. Rather, we are dealing with an unstructured grid. So first statement is false, second statement is again false. But in third statement, what is given? Grid refinement at the wall boundaries. So near the walls, we have seen that grid refinement has taken place. So third statement is true. Option 1 and 2 are false, but option 3 is right. So coming back to the options, option A 1 only, option B 2 only, option C 3 only, option D 2 and 3. So on that basis, what we can say, only third statement is right. The first statement, it is mentioned that local grid refinement in an unstructured grid. So although the given figure has an unstructured grid measurement, unstructured grid, we cannot say there is a local grid refinement. Rather, the grid refinement is only near the walls. And the second statement, it is mentioning that local grid refinement in a structured grid. This statement is completely false because it is not a structured grid and there is no local grid refinement as well. Third statement, however, is true because grid refinement at the wall boundaries. Here we can clearly see that there is grid refinement only near the wall boundaries. What do we mean by grid refinement? The grids have reduced, grid sizes have reduced near the walls. Like we have refined it into a smaller structure. So because when we refine the grids near the walls, now we can get a more accurate result near the walls. So we generally prefer to have a refinement near the walls. Like one here we have 4 refined layers. So 4, 5 or some number of layers near the walls would be refined. And therefore the right option is option C. So option C 3 only is the right answer. So answer is given by C. Now let us go to question 4. In question 4, it is asked that with reference to the grid and domain shown in figure 1a, that is this figure, if Dirichlet boundary conditions are specified over the left and right boundaries, so left and right boundaries, we have Dirichlet boundary condition and Robin boundary conditions are specified on the top and bottom boundaries. So top and bottom boundaries, we have Robin boundary conditions, which is like having mix of Dirichlet and Newman boundary conditions over certain regions. Like it will be having a Dirichlet till this and Newman till that, like that mix will be there. And how many algebraic equations need to be solved simultaneously when solving a steady diffusing equations using finite difference method. So how many algebraic equations we need to solve? So here we are using finite difference approach. So here we will be calculating everything at a grid point. So here, if that is the case, we first need to identify how many cells are there. So like for example, this is a rectangular structure and we have 1, 2, 3, 4, 5, 11, 12. 12 cells in the or 12 grids in the horizontal direction and 5, 6, 7, 8, 9 and 10. 10 grids in the vertical direction. So 10 comma 2 or 12 cross 10 or 10 cross 12 cells we have on the whole. That is, we have 10 cells, 10 grids in the vertical direction and 12 grids in the horizontal direction. So we have 120 cells roughly. Now what we must do, we will be having 10 into 12. So number of grid points will be 10 plus 1 into 12 plus 1. That is 11 into 13. So we have roughly 11 into 13, 143. So I'll just put it over here. So what we are dealing, we have 10 cross 12 cells. So since we are using finite difference approach, we have 11 cross 13 equations. I hope you remember, because we will be using the equations in all the points. So that many equations we will be having. So what is asked in the question, if Dirichlet boundary conditions are specified over the left and right boundaries and drop-in boundary conditions are specified on the top and bottom boundaries, how many algebraic equations we need to solve? So here we have 143. So 143 total number of equations. So left and right we will be using the Dirichlet boundary condition. So those values are known. So we need to now subtract that. So it is 143 minus 11. So roughly we get 121, because we are subtracting in this side and that side. So it is like, and we now have the grid points at this particular region. Once again, 1, 2, 3, 4. Here. Now in the top and bottom we are using Robin boundary condition. So Robin boundary condition, what we do is that we use Dirichlet in some zones and Newman boundary condition in some zones. So there will be roughly some values will be known and some values will be unknown still. So those things would be coming between plus or minus 5 we can take. So it is like between 115 and 125. So roughly here we got 120, and therefore here we are saying between 115 and 125, because in Robin boundary conditions we are not sure in which zones it will be. So we are saying plus or minus 5. So there in the on that condition we have between 115 and 125. So I hope it is clear now. Now we'll go to answer is option C. That is like 115 and 125. So now let us go to question 5. So I guess like time is 4 now. So we can take a 5 minutes break and come back, and we'll solve the rest of the problems. Like we'll come back sharply by 4, 5. Thank you. So yeah, we'll now start back. So in fifth question, it is asked regarding figure 1b. So in with reference to the grid and domain shown in 1b, if directional boundary conditions are specified over the left and right boundaries and Robin boundary conditions are specified over the top and bottom boundaries, how many algebraic equations do we need to solve simultaneously when solving a steady scalar transport equation using finite volume method? So here it is an unstructured mesh, so we are going with finite volume method, and now we need to find how many equations do we need to solve. So here again we are applying Dirichlet boundary conditions near the left and right boundaries and Robin boundary conditions on top and bottom boundaries. So in finite volume method, if you remember, we will solve the equations at the cell center. In finite grid method, however, we are solving at the cell vertices or something. But in finite volume method, we will be solving the equations at the cell center. So here we need to identify how many cells are there. Only then we can say how many equations we need to solve. So here we have 4 layers and here 4 layers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 into 8, 88 equations we need to solve along the walls itself. So and rest of the equations we need to find out how many cells are here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 36, 37, 38, 39, 40, 41. So roughly it would be 82. And here we have 88. 88. So it would be like 160 equations. So we can say that it would be more than 150. So because we are applying the boundary conditions, there might be some less equations that we need to solve. But on the whole, we have around 160 equations because we are now counting the number of cells in this particular grid. So since it is coming closer to 160, we can say that look at the options. Option A, it is fewer than 100, false. Option B, about 120, again it is false. Option C, about 140, again it is false. Option D, more than 150, which is true because here we are solving number of equations are more than 150. Like we are getting around 160 plus. So we are roughly saying as 150, like there might be some calculation errors, counting errors. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Like 40, 40, 80 and 88. 168 or 169, something like that. Number of equations will come. So here we are saying more than 150 equations we need to solve. Because first thing, it is an unstructured mesh and therefore we are using finite volume approach, and since we are using finite volume approach, we will be solving the equations at the center of the cell. So we need to count how many number of cells are there in the particular figure. So we are getting around close to 160 something. So we are saying it is to be about or more than 150. We are not saying closer to anything, we are just saying more than 150. Because if boundary conditions are, it would not be affecting, but still if there are anything, it would be coming less than that. So here it is more than 150 is the right answer. So accordingly we are just choosing option D. Option D is the right answer. So now let us go on to question 6. In question 6, it is mentioned that with reference to the grid and domain shown in figure 1a, which is a structured grid, which of the following statements is true about the solution scheme? Option 1, local grid refinement is possible. Option 2, local grid coarsening is possible. Option 3, multi-grid approach is possible. So figure 1a is this, so we need to identify which of the following is possible. First one, local grid refinement is possible. So locally we can refine it somehow because it is already like local grid refinement is there. Further refinement is also feasible at times. So one is true. Second one, local grid coarsening is possible. So if refinement is there, we can coarsen the grids as well. That might or might not lead to our solution is the next issue, but local grid refinement and local grid coarsening is possible. Third one, multi-grid approach is possible. Again, multi-grid approach is possible because multi-grid approach is nothing but we will be solving the solution and we'll be using a series of grids to get the solution. So that can also be done. So since it is a structured mesh, we can go with local grid refinement or local grid coarsening, whatever we want, it is possible in this. So all three are possible. So looking at the options, option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So what we were seeing, all three statements are right. So that is given in option D because we can do local grid refinement and local grid coarsening and multi-grid approach is also possible. So all three are feasible for this particular grid. So we can say that option D is the right answer. So answer is D. We now go to question 7. In question 7, it is mentioned that with reference to grid and domain shown in figure 1b, that is this particular one, which of the following methods can be used to solve the algebraic equations resulting from the discretization of scalar transport equation with constant coefficients. So here we are using this is particular figure is an unstructured mesh and we are using mathematical methods to solve the resulting algebraic equations which we have obtained after discretization of the scalar transport equations with constant coefficients. So since it is an unstructured mesh, we are going with constant volume approach and we use, finite volume approach, not constant, finite volume approach, and we get the discretization and we get the algebraic equations. So after that we need to solve those equations, right? So which of the schemes given would be suitable? First one, it is ADI scheme, that is alternating direction implicit scheme. So alternating direction implicit, if you remember, it would require certain tridiagonal matrix format. And second one is SOR scheme, successive over relaxation scheme. And third one is LU decomposition method. So in given options, if we consider that, first one, it requires a certain condition to be met, whereas option 2 and 3 does not require certain conditions. So if that is the case, ADI scheme, it requires tridiagonal matrix, so which we do not know if we can obtain from the discretization. So since it is an unstructured mesh, the chances of us getting that format, what do we call, tridiagonal format, is less. The chances for us to get that is less or closer to 0, we can say that. So first one is not possible, whereas in the second one, successive over relaxation and LU decomposition method, there is no such criteria to be met for us to get the solution, or for us to use the method itself. It is there is no restrictions in SOR method and LU decomposition method. So 2 and 3 we can use, but one has certain restrictions which is making it impossible to use that method. So options, we look at the options now. Option A, that is 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So looking at it, we can say that option B is the right answer because it is having 2 and 3. that is SOR scheme and LU decomposition scheme as the options. So we can say that option B is the right answer. Why? Because the given mesh is an unstructured mesh, and also for unstructured mesh we do not know how we will be getting this coefficient matrix, and ADI cannot be used in such cases, but we can use SOR scheme and LU decomposition scheme because it is a generalized methods which we can use it in almost all cases. Why we cannot use ADI is that ADI requires tridiagonal matrix condition to be met, which is not feasible over here. So 1 is false, 2 and 3 are right, which is correctly given by option B. Answer is therefore option B. Now let us move on to the next question. In question 8, it is asked that which of the following are the consequence of transformation of an unsteady scalar transport equation into a non-orthogonal curvilinear coordinate system. So which of the following are the consequence of the transformation of an unsteady scalar transport equation into a non-orthogonal curvilinear coordinate system? So similar question we have seen in the last class itself. Like in that question I remember it was asked regarding a transport of a elliptic equation and whether any mathematical nature changes. So in that question itself we have seen that mathematical changes does not happen. So here it is option given are option 1 is cross derivative terms appear, and second one mathematical nature changes from hyperbolic to parabolic. So right answer is option 1 is true but 2 is false. So option A it is 1, option B it is 2, option C both 1 and 2, option D neither 1 nor 2. So option A is true because cross derivative terms appear but mathematical nature does not change from hyperbolic to parabolic also. So answer is option A. Let us now go to question 9. In one second. In question 9, consistent evaluation of fluxes in a finite volume method means option 1 at least second order accuracy in evaluation of fluxes, option 2 evaluation of fluxes at midpoint of phases, option option 3 flux conservation across common phases of adjacent cells. Just give me a moment actually. Okay. Consistent evaluation of fluxes in finite volume method means at least second order accuracy in evaluation of fluxes at midpoint of phases, flux conservation across common phases of adjacent cells. So we are saying that there is a consistent evaluation of fluxes when we are using finite volume method. So it doesn't mean that second order accuracy in evaluation of fluxes is maintained, or it doesn't even mean evaluation of fluxes at midpoint of phases. Rather, what we are stating is that if there is a common phase between two cells, there a flux conservation is there. For example, here if this is a common phase between these two cells, here we will be using finite volume approach only. And here we are saying that the flux conservation is there across the common phase of the cells. So here it is flux conservation is there is no loss or anything. So that is what we mean when we say consistent evaluation of fluxes in the finite volume method. So option 3, that is third statement, is the right statement. So coming back to the options, we have option A 1, option B 2, option C 3, option D 1, 2 and 3. So answer is option C because third statement only is right. And after that we now go to question 10. In question 10, it is asked that which of the following statements is true about the Bowyer-Watson algorithm for Delaunay triangulations. So options are: all boundary grid nodes are inserted first. Second one is all nodes are inserted randomly. Third one, fewer number of triangles are produced than in the advancing friend method. So we all know that in Bowyer-Watson algorithm for Delaunay triangulation, we insert the nodes randomly, and therefore second statement is the only right statement. It is not that all boundary grid nodes are inserted first and then we do, or fewer number of triangles are produced than in our advancing friend method is also false. So here we are using random insertion of the nodes. So that is what happens in the Delaunay triangulation while we are gridding the system, like grid generation approach. So there we use a triangulation technique. So there we have the random insertion of the nodes. So in grid, that is what happens. So and then we have question 11. In question 11, it is asked that following possibility can happen during advancing friend method of triangulation. First one, triangles of higher aspect ratio are created. Second one, domain outside boundary is partly included during triangulation near concave boundaries. And third one, domain outside boundary is partly included during triangulation near convex boundaries. So here we are not including any domain outside the boundary when we are doing the triangulation for concave boundaries or convex boundaries. Rather, in advancing friend method of triangulation, aspect ratio is high. Aspect ratio is nothing but the longest length to the shortest length. So here we can say that aspect ratio are higher in the advancing friend method. But rather we cannot comment on domain outside the boundary is included or not. We cannot comment. So triangles of higher aspect ratio are created is a true statement. So first one is a right statement. Second and third statements are false. So accordingly, option A 1 is true. Option B 2, that is false. Option C 3, that is again false. Option C 1 and 3, because it is including 3, that is a false statement. Option D 2 and 3, again it is false. So now answer is option A because first statement alone is the right statement. We now go into question 12. In question 12, the following possibility can happen during Bowyer-Watson method of triangulation. First one, triangles of higher aspect ratio are created. False because it happens in advancing friend method of triangulation. Second one, domain outside boundary is partly included during triangulation near concave boundaries. That is true. And third one is domain outside boundary is partly included near the triangulation of convex boundaries. So here in Bowyer-Watson method, what we do is we insert the nodes randomly. So we are saying that there are chances for the domain outside the triangulation. Domain outside the boundary is partly included when we are dealing with the concave boundaries. But first statement belongs to the advancing friend method. So the thing in Bowyer-Watson method is we insert the grid nodes point randomly, and we sometimes it includes the domain outside the boundary partly. So the Bauer-Watson algorithm is nothing but it is an insertion algorithm. So it is nothing but inside the Delaunay mesh we insert the points randomly and retriangulate the mesh. So it includes a series of steps. So in that steps I'll just read out the steps followed. So it generates a set of grid point locations for the domain of interest. So that grid point location include all the boundary points and all the interior points as well. So there are a number of ways of carrying out the grid point generation. First one is a random number generator. So that's why we say that grid points are generated randomly, or some other techniques are also there, structured grid generators such as TFI or elliptic generations, and domain methods based on domain decomposition, whatever, self-adjusting method, and so on. So after that, an initial super triangle that completely encloses the entire domain is created. This may be valid triangulation. Simplest geometry is a super triangle, and from that we insert a mesh point from the list established in the step 1. That is, in step 1 we generated a random number of grid points, and in second step we have created the super triangle, and after that in third one a mesh point from the list that is we have generated randomly is inserted into the existing triangulation, and after that we delete the triangle that fails the circumcircle test, and this process will be continuing. Like after that, after the deletion, a search of the neighbors from the first deleted cell is conducted to determine if any other cells have violated circumcircles. That is the criteria to check if it falls into that cells. And if a neighbor cell is deleted, common phase between neighbor and the first deleted cells must be removed, and search proceeds the neighbor of the cells. So on that basis we have that given. So here the domain outside the boundary might be included partly for the concave boundaries, not convex boundaries. So answer is option B. That is second one is the true, because domain outside the boundary is partly included during triangulation for the concave boundaries. Now let us go to question 13. In question 13, it is asked that which of the following can contribute to numerical errors in a CFD solution. First one, truncation. Second one, grid generation. Third one, solution of algebraic equations. So when we are using CFD schemes, what we are doing is that we are converting the partial differential equations for the, those partial differential equations are nothing but the governing equations of the fluid flow, and we are just converting the partial differential equations into an linear algebraic equations using some numerical techniques, and then we are solving those linear algebraic equations using the numerical techniques. So what are all the errors that can come into the solutions? First one, truncation. So yes, it comes into picture because when we are using the what is it discretization schemes, we are truncating certain terms. So based on that we get the order of accuracy of the system, but still it can contribute to some form of errors. Second one, grid generation. Again this is true because we are dividing the grids, and if depending on the grid size, and we can say that there might be some loss in information. The grid size is nothing but how much, how far the information is traveling. So if it is near, it will be completely traveling. The information will be completely traveling. If it is far, that is in coarser grids, there will be like some loss in information. So second grid generation again contributes to some errors in numerical errors. Third one, solution of algebraic equations. Here again we are using various mathematical numerical methods like Gauss-Seidel method, Jacobi method, ADA method, SOR method we have seen. So every method is unique, and again there will be some things happening behind. So solution of the algebraic equations will also contribute to some form of errors. So on that basis we have 1, 2 and 3. So all three statements are right. That is truncation error, grid generation and solution of algebraic equations. All of them contribute to the numerical errors in a CFD solution. So answer is option D, 1, 2 and 3. So in option A it is 1 only, option B it is 1 and 2, option C 1 and 3, option D 1, 2 and 3. So our right answer is option D. Now let us go to question 14. In question 14, which of the following decreases when grid sizes decrease? That is, number of grid points is increased. Option 1, truncation errors. Option 2, asymptotic convergence rate. So truncation error is nothing but how, like, we are neglecting certain terms. Depending on the order of accuracy, if we can, like, we neglect delta x cube term or delta x square term or delta x power 4. So those are the contributions of the truncation errors. So imagine if grid size is decreased, that is delta x is decreased now. So if delta x is decreased, those truncation error terms would also decrease obviously, because delta x powers delta x square and delta x cube. If delta x is large, those would be large. If delta x is small, those would be small as well. So since truncation error is directly proportional to delta x, decreasing in the grid size and increasing the number of grid points decreases the truncation error, and asymptotic convergence rate also would be decreased. And therefore options are option A, that is 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So we know that answer is option C, that is 1 and 2 are right. In question 15 we have, which of the following steps is unique to structured grid that is not there in unstructured grid approach to solving a CFD problem? So what is the uniqueness in structured grid which is absent in the unstructured grid problem when we are dealing with getting a solution for the CFD problem? So the first one is coordinate transformation, second one is finite difference approximation of derivatives, and third one is banded coefficient matrix, fourth one is iterative solution of algebraic equations. So the first one is coordinate transformation, that we can easily do in structured grid, which cannot be done in unstructured grid, that is r theta z, or can be transformed into xyz like that. It can be done in structured grid, but it cannot be done in unstructured grid because there is no direct relation between the adjacent cells in the unstructured grid. So we need to create a separate cell list in unstructured grid, so it is not possible to for coordinate transformation in unstructured grid. So one is true. Second one, finite different approximation of derivatives. Again this is true because in structured grid we can identify the adjacent cells based on some ijk information, which is not possible in the unstructured grid. In unstructured grid we cannot identify the neighbor cell based on the ijk information. So we need to go with the finite volume approach. Finite difference approximation is not possible. Third one, banded coefficient matrix. So in structured mesh we can get a banded coefficient matrix, but in unstructured grid we cannot get that, because we have seen in the previous examples itself like how unstructured grid mesh would look like. So this is a structured grid, this is unstructured grid. So we can say that banded coefficient matrix, that is some pattern in the coefficient matrix, we can get in option, that is structured mesh, that is in A grid we can get, but in B grid we cannot get the banded coefficient matrix because we are using finite volume method, and we cannot say that we will be getting anything. So banded coefficient matrix is unique to structured grid, which we cannot get in unstructured grid. And last one, it is iterative solution of algebraic equations. Again, but in iterative solutions, however, we can use it for structured grid or unstructured grid. It would not be an issue. Like here, Gauss-Seidel method is an iterative method which we can use in structured grid or unstructured grid. Both can be applicable. So it is not a uniqueness to the structured grid. Which is here, what we mean by uniqueness is that it is present only in structured grid, but it is absent in the unstructured grid. The fourth one is false. So 1 is right, 2 is right, 3 is right, 4 is false. So options, if we look at it, option A 1, option B 1 and 2, option C 1, 2 and 3, option D 1, 2 and 3, 1, 2, 3 and 4. So option A, it is 1 is right, option B 1 and 2 is right, but in option C it is 1, 2 and 3. So it is including everything, so right answer is option C. In option D, it has inclusion of the fourth statement as well, which is false because iterative solution of algebraic equation is common to both structured grid and unstructured grid. So we cannot say that it is an uniqueness to a structured grid. So that one is false. Option D is false. So option C is the right answer. So yeah, that's it. I mean, these are the questions for today's class. Yeah, thank you. I think this will be the last class for this session, unless until there is some summary type of class, but mostly it will be repetitive of whatever we have seen, and most probably it will not be there. If it is there, it will be informed from NPTEL, but there will be no unique concepts being discussed or no unique problems being discussed in that class. So these are the problem for today's class, and mostly this will be the last class. So I just want to thank everyone for attending. If there are any doubts or any questions, I would like to take now.
Hello, ma'am.
Yeah.
Regarding this exams, we have how many questions? Like it is like MCQ only, right?
Yeah,
It's
it will be like MCQ.
for 100 marks. It will be like 1 mark each question, or how it will be?
I mean, it depends. Actually, I'm not sure how of that, but mostly it will be MCQ questions. That much I know, but I'm not like sure of the points or.
Okay, because for us assignments they have given like everything as 1 point.
Um,
So
yeah, like it will be like solvable in 3 hours, and it would not be like 100 questions like that.
mm,
But I'm not sure of how the question is prepared, and so I have no idea on that aspect.
oh, okay.
Yeah.
regarding this questions in exams, whether like is there any um like approximation like from assignment questions, how many percentage the questions will cover? Is there anything like that or?
And there is no, so, I mean, your grade wise, you know, right? There is some percentage
No,
from assignment.
no. I'm asking
In
like for
exams,
exams.
okay.
Yeah, for this exam next week.
That I'm not sure. Like similar questions can come, but again, I'm not sure of which. I mean, how many questions or what percentage of questions. But
Mm-hmm.
if you practice the assignments, it would be like almost it has covered what can be coming.
Mm.
Yeah. So that's it. I mean, I'm not sure like what sir has taken. I don't know anything in regards to that.
Okay. Okay.
Yeah. Thank you.
Thank you.
Yeah. Thank you as well. Like, thanks for session. Yeah. Thank you. Thank you. Yes. So that's it for today's class. We can close the session now.